Okay, so here we have a do now. That is a big time review question. This is from all the way back when we did mechanics, but it will definitely lead into what we're doing today. So bear with me. Okay, so we have a 10 Newton object lifted 4 meters. So we have 10 newtons. 10 Newton object lifted 4 meters in the air in a time of 2 seconds. First question says how much work is done. So if we remember, work is equal to force times distance. And the force, since this thing weighs 10 newtons, is going to be 10 newtons, because that's how much you have to apply to lift it up. Then we got 4 meters it's being lifted. So we have 40 Newton meters, or remember we could also say that's joules. Now, power, if you remember, power is work per unit time. So this is going to be 40 joules per, and it says 2 seconds. So this is going to be 20 joules per second, or hopefully you remember, that would be watts. Okay, so simple enough. This is a nice, easy review question of mechanics. Hopefully you remember all that. Now, this is the formula we're dealing with. The question is why would I bother to bring this up? Well, power is something that's very often discussed in electrical circuits. So what we need to do is we need to convert this mechanics formula into something that's a little bit more user-friendly for circuits. So here's how we're going to do that. We're going to take this guy. We're going to remember that voltage, or potential difference, is work per unit charge. So then we're going to say that work is equal to voltage times charge. Okay? Now we can take this, to bring it back to the formula. So now we're going to have P equals voltage times Q over T. Now, Q over T, we hopefully remember, is current. So now we have this. This is a very user-friendly formula for us. We happen to know the voltage going through a particular device, or rather being used by a device or lost in a device, and the current going through that device. Well, then we can find out how much power is generated by that. Now, we don't always have V and I, so our reference table is nice enough to give us this. P equals to V times I, great. But I squared R in case they only give us I and R and don't give us V. And V squared over R in case they don't give us I. We can use this formula. Now, because you know how much I love giving you formulas and not explaining to you where they came from, I'm going to explain that real quick. So if we start with P equals VI. Now this one does not have V in it. So what we're going to do is we're going to try to take V out. And how are we going to do that? Well, we're going to use our good old friend V equals IR. Right? So if I take IR and put it in for V, I have P equals I times R times I, which I times I is I squared R, and we have power equals I squared R. Now, the last one, we got P equals VI, so we're going to start with that. This one doesn't have I in it, so we're going to take out I and put in what it's equivalent to. Now, we'll put V equals IR down here. If I solve this for I get I equals V over R. So I take out I, put over that, and I get V times V over R, which is V squared over R. Ta-da! Okay, so this is just, and we've had a couple of these before during the year where, depending on the information they give you, it's just 3 different variations of the same formula for the same thing. So, let's do an example. Here we have example 1. It says a toaster has a current of, again, milliamps. Remember, I told you that's going to happen often. So we got 4 milliamps. So 4 times 10 to the negative 3 amps. And a resistance of 8,000 ohms. And the question just says how much power is generated by the toaster. So we're looking for power. So I have P, I have I have R. So I'm going to say P equals I squared R. Okay, so P equals 4 times 10 to the negative 3 squared times 8,000 ohms. So, I'll give you a second or two to do math on that. So we got this, right? And then this is going to be, let's see, 8 times 16. Or I guess we could argue that this is just 0.128 watts. Okay. Let's just do a second example. I'll give you a little bit more time. I'll let you kind of do this a little bit more on your own. I will just start silently and slowly writing things on the board. Okay. Now, what I do want to point out is the way this was worded, because sometimes they like to do this on Regents level questions. At what rate is energy being dissipated or used? Rate at which energy is being used is just energy or work per unit time. So this is power. You have to be mindful of that. Okay? So we are just looking for P despite the weird wording of it. Okay, so I'm assuming or hoping you were doing that on your own as I was doing it here, but we had 100 volts squared over 5,000 ohms. 100 squared is just 10,000, right? And then we divide that by the 5,000 ohms. We got rid of the 3 zeros in each. 10 divided by 5 gives you 2 watts. Okay, now here's a proof that the Regents exam, or the people who make the Regents exam, don't think us regular people are very smart. Immediately on your reference table, underneath the formulas that we came up with before, so these guys, they write these. Now, we said before, we based our whole argument off of power is work over time. So all they're doing here is they're rewriting it as work equals power times time. Now, we are going to think of work in this case. Instead of work, we're going to think of this as electric energy, because it's really how much work that electrical device can do. I'm just going to rewrite that. Okay, so this is a formula for electric energy, so all they've done is they've solved the power formula for W. Now, because they don't think we're terribly bright, they then said, well, we know P is equal to VI, so we need to tell them that work is equal to VI times T. And then they did the same thing here. Since power is equal to I squared R also, it's I squared R times T, and same thing here. It's equal to V squared over R times T. So let's just try a quick question on that to show you one or two little pitfalls they sometimes get you with, and then I'll set you loose on doing some questions. All right, so we got a 12 volt battery. So we have a voltage of 12 volts. We have a current of 0.2 amps, and it says a time of 2 minutes. They love to do this on the test. Remember, we never ever use minutes. We use seconds. So this amount of time in seconds is going to be 2 minutes times 60 seconds per minute. That's going to be 120 seconds. Okay, so now we have that, and it says how much energy is used. So energy and work, again, synonymous with each other. So we got V times I times T. So we got energy is equal to 12 volts times 0.2 amps times 120 seconds. And that should come out to be, unless I'm doing my math wrong, 28.8, because we got 144 times 2 would be 288, but it's not 2, it's 0.2, so it's 28.8 joules. Remember, this could be joules. Okay, so that's a reasonably simple set of questions. It kind of adds on to the series circuit stuff that we did last time. So remember, now we've done series circuits. Okay, so eventually this idea of work and power done by devices in a series circuit is going to kind of attach to that. Tomorrow I'm going to put out a quick lesson on the devices that are put in, or I guess devices for the sake of measuring, that are put into these circuits. So we're going to talk about voltmeters and ammeters. I know I mentioned them briefly in my lesson about series circuits, but we're going to talk about them in more detail. This one, there won't be an assignment necessarily for it. I'm just putting it out there so that when I start mentioning it on Wednesday, when we start talking about what's known as parallel circuits, you guys will have an idea what I'm talking about. After parallel circuits, or on the same day as parallel circuits, I'm going to give you an assignment. And then Friday, and we'll probably stick with the same time as we did. So since this lesson is for 2 different classes, I'm going to hope that you guys remember the times you had. I think it was 10 o'clock and 11 o'clock. I don't remember which class was which. But I'm going to hope that you guys remember. I will obviously send out the links on Thursday so that we know exactly who's coming at 10 and exactly who's coming at 11. All right? So that's the week in a nutshell. And I will talk to you guys tomorrow. Enjoy.